Okay, so we've talked about diamagnetism, and now we're going to look at paramagnetism and ferro. These two types of magnetism depend on the concepts of electron spin, the accompanying magnetic moments that are coupled to spin, and the ferro is going to depend on the formation of domains. So all of these play a critical role. To review some of the concepts, I've just repeated this slide from a previous talk. What I want to remind you of are these various definitions and how they go together. Chi sub m is the susceptibility, and it's the magnetic susceptibility in our case, thus the m. Mu is the permeability. Mu is equal to 1 plus chi sub m times mu sub 0, and we call this quantity here mu sub r, like that. It's the relative permeability. For linear material, we have B equal to mu sub h, and so we'll be using this. Going back to B equaling B0 plus a term that has the magnetization in it, the B0, it would be mu 0 times h. So this would be the applied h, which generates a B0, and this would be like a field that's outside in space. However, it penetrates into the material, and so it's in that region of where you have material. And by the way, this B here corresponds to B inside, unless capital M is equal to 0. Then you only have this term here. If we substitute in how M depends on H, if you recall, it's equal to this quantity here. It's chi sub m times H. So all we've done is put in M in terms of H. If we factor out the H, then we have the factor 1 plus chi sub m times mu 0 h. So let's rewrite this. If we have B equaling B inside, as I've mentioned, that's B0 plus mu 0 m, and this could be written as B0 plus this quantity here, which depends on H. The B inside, B0 plus mu 0 chi sub mh, allows us then to call the B mag, this term right here, and so here it is right here, here's B mag. And if we just swap these two factors here, you'll notice that what we have here is B0. If we look at just the B mag, it's equal to chi sub m times B0. So I've rewritten that here. So we've just got this term here, or this equation. For linear materials, we have B mag either parallel to B0 or anti-parallel to B0. This type of material here we would call para, and as before, when this is anti-parallel to B0, we have dia here. If we look at the sign of chi sub m, that determines whether or not we have para or dia. So remember, for dia, we have this quantity here, chi sub m less than 0. Here's B mag, which is now going to be negative because of the negative chi sub m. So B inside will be B0 plus a minus a negative quantity, and so here's B inside again in terms of 1 plus chi sub m. The net result is, because this is negative, that's going to reduce B inside from B0. So we have this expression here. Realize that chi sub m is very small, so this will end up being close to B0, but it will be slightly less. If we look then in terms of the magnetization that develops in the material, it will be in the opposite direction to the applied magnetic field. So if m is linear, we have a constant slope, but it will be negative chi sub m. It goes to 0 at h equals 0. So here we are here, the magnetization of a diamagnetic material as a function of the applied h is a linear function with a negative slope because of chi sub m being less than 0. As a result, the magnetization is in the opposite direction to h. It's very small because of chi being very small. Here's a repeat of all these parameters here. And we've talked about the various types of behavior of the diamagnetic materials. Let's go back to para now. The first thing to realize is that electrons interact, and Pauli's exclusion principle says that each possible electron orbit in an atom can be occupied by up to 2 electrons with opposite spins. And materials or atoms that do this are called fermions. If we have paired electrons, they will pair in such a way that the total spin angular momentum is equal to 0. And so if you take the m spin here in this direction, m spin in this direction, if you sum those up, you'll get 0. And so we have opposing spins. If we have a single electron, so we have an unpaired electron, then here we sit with this m spin. Here's the angular momentum here. If you look at this, then you have a non-zero m, so we have a single spin with a non-zero. So the atom itself has a non-zero magnetic moment. Just to remind you, it's a little more subtle than the way I presented this here. If we look at the alignment of the spin in a magnetic field, basically it is in an orientation that I show here. When you apply the magnetic field, this spin vector orbits like this, turns like this. Therefore, the dipole moment associated with that spin will also rotate. Normally what's going to end up being important is the z component of the magnetic moment. And so if we flip it, then we'll have it in the opposite direction. So we still have the process of having a magnetic moment with a strong component in the z direction. If we have the unpaired electron spins in their electron orbitals, these will have a permanent magnetic dipole, even in the absence of an applied field, due to this m spin. Okay, so those are the atoms. In general, this occurs in atoms or molecules with odd numbers of electrons. There are some exceptions, and one of them is the oxygen molecule. What happens then is that if we're sitting in, say, room temperature or higher, the permanent atom-molecule dipoles are randomly oriented. They do not interact with one another, and the reason is because that interaction is so small. And so due to thermal agitation, we get random orientation. The net result is that the magnetic moment is equal to 0. If you apply a magnetic field, the dipoles will tend to align with the applied field. A net magnetic moment in the direction of the applied field results. And how does that happen? Well, remember there's a torque on a magnetic moment. The magnetic moment of the electron will be pushed or twisted by the applied B field because of this torque. Okay, so if you have a material of a large number of these paramagnetic atoms or molecules, you'll end up with a magnetization. It will have a direction parallel to the external field. So that's stated here. The resulting paramagnetism, M is aligned with B0, is weak, it's linear in applied B sub H, and disappears when the field is removed. So there's no permanent paramagnetism. So if we look at the results on the equations for B, so B inside, this is the same material that I gave you before, and now we're taking a look at this equation here, where we have B0 plus B mag. And for para, B mag is parallel to B0. So what that does is it makes chi sub m greater than 0, and that'll be para. So here we are. If chi sub m is greater than 0, then B mag will be in the same direction as B0. So that's what we mean by aligned. It's parallel rather than anti-parallel. Rewriting B inside then in terms of chi, here's our B0 plus chi sub m B0. If we then factor out the B, we would have B inside equaling this quantity here. This would be 1 plus chi sub m, which is a positive number. So we end up with the B field inside getting slightly larger than B0. It's only slightly larger because this is a small number, positive number. So that's paramagnetism. If we look at this and compare it with the materials of electrical dipole types, so dielectric materials, in both cases the torques on the dipoles cause alignment of the dipole vector parallel to the external field. If we look at what we just derived for the magnetic case, if we have paramagnetism, we have B going up. So if we have paramagnetism, we have an increase in the B field inside from the applied field. In the dielectric case, if you remember, E inside actually goes down. There's a shielding effect due to the polarization of the material. The way that comes out in terms of equations is that the E field is the applied field divided by 1 plus chi sub E. So as a result, for basically all dielectrics, this is positive, and so you end up with E going down. So we have this difference in behavior between dielectrics and magnetic materials. So if we look then at the plot of the magnetization with H, when we're at 0, we have total disorder, and so we have no magnetization. We're at the origin here. As we apply a magnetic field, it will try to align. And I didn't emphasize this, but I should, is that you're fighting thermal energy. For most temperatures, the thermal energy dominates. And so as a result, you don't get perfect alignment. You get partial alignment. And because of that reason, this is a small number. But it still increases with H. If you were to go to lower temperatures, you'd have a larger chi sub m, and so this would be a steeper curve. One or more electron spins is unpaired in the paramagnetic case. The atomic net moment is not 0. The paramagnetic chi sub m is reversible, so if you go up this curve and then take H back down, it comes right back down here along this curve, and there's no deviation from that behavior. For very large H or very low T, you will approach alignment of all the moments. The other thing that we should realize, what I just said here, is that chi sub m is temperature dependent. So lower temperatures, bigger chi sub m. Here's the actual temperature dependence of a paramagnetic material. This was derived by Curie-Weiss, and here it is. It has a 1 over T dependence, and it has a constant theta, which is the paramagnetic Curie temperature. It's very small, so it's near 0 K for most magnetic solids. Notice that it's a temperature, so it has this form here. If you have then the quantity here very small, you really don't see behavior of any kind of a threshold. It's really 1 over T unless you go to extremely low temperatures. And this constant here, C, is material dependent. So depending on the material, you'll have this constant here, which will basically determine where this curve sits, like this, like that. At high temperatures, you notice that the para is getting smaller and smaller. If you remember, dia is not temperature dependent. And so as a result, if you go to sufficiently high temperatures, you're able to get rid of para and start to see dia in a paramagnetic material. If you don't have paramagnetic behavior, you only have dia to deal with. So let's restate some of these things. We have the parallel nature of the magnetization that's induced by an external field, and they're in the same direction. And we have this case where we have an appearance of paramagnetic materials if you have unpaired spins. Realize that these are often embedded in a material, and sometimes you have molecular complexes which prevents coupling between them. And what that does is it prevents the formation of domains. So you have isolated atoms or molecules that give you this behavior. So each one is independent. Examples of some paramagnetic materials, there's several metals, tungsten, aluminum, sodium, platinum, and many others. If you take iron, ferromagnetic material, so iron, nickel, cobalt, and can isolate normally by attaching them to big molecules, then you'll end up with paramagnetic behavior, even though it's a ferromagnetic atom. Just to repeat, M is very small. It's larger than the dia, so it dominates at low temperatures, but it is still small. The most classical paramagnetic atom is hydrogen, and the reason is that it has an unpaired electron because it only has one. So what about the orbital magnetic moment? Well, there we have to go to quantum mechanics. So what I just said was the single electron with its spin provides the magnetism. The ground state of hydrogen, if you remember in quantum, is the L equals 0 state, and we call that the S state. Now remember, this S is not the spin. This is the nomenclature for L equals 0. So what that means is the orbital angular momentum, which we sometimes label as capital L, does not contribute. In quantum, remember, the atomic dipole due to orbital motion is proportional to L. So if L equals 0, we end up with 0 orbital magnetic moment. So as a result, the spin is the only important one. A lot of atoms have S states even when they have this unpaired spin, and so we don't worry about the orbital contribution to the magnetic moment. It's all due to spin. Here's some minerals that have chi-sub-M's that are positive. You can see they're small. These are minerals that have usually some sort of a magnetic material in them. You notice this has iron. This I don't have any idea what it is. Here's another iron compound, and here's another one that has both iron and chromium. But you can see here that they all have positive, non-zero chi-sub-M's, and so therefore they have paramagnetic behavior. Another comparison is looking at the chi-sub-M and the relative mu sub r, which, if you remember correctly, is 1 plus chi-sub-M. These are really small numbers, and so these differ very little from 1. Well, here's gold and quartz. Those are diamagnetics with a minus sign, and so here's the deviation from 1. You can see is very, very small, but that's the mu sub r. This is gaseous O2, oxygen, at standard temperature and pressure, and that gives you this value of positive chi-sub-M. Here's the positive change from 1 for mu sub r. Now notice if you go to liquid oxygen, because of the much, much closer density of dipoles, just because of the liquid nature over gaseous, we have a bigger chi-sub-M, quite a bit bigger, and that results in a shift of the deviation from 1 towards the decimal point. So you have this value of mu sub r. And if you've ever seen it, you can put liquid oxygen between the poles of a strong magnet, and it will basically stick between the two poles. So let's summarize the para and dia. Remember that both para and dia effects happen at the same time if you have para. If we look at the size of these effects, the dia is the weakest, and it shows up in materials where you have intrinsic atomic magnetic moments that are small. These are usually atoms that have even numbers of electrons. The best example of that is helium, so it has 2 electrons that pair. Or if you have paramagnetic materials that you've heated so that the thermal agitation disrupts the alignment of dipoles due to the unpaired spin, that ends up leaving dia alone. So dia exists in all of these systems. The magnitude and type of response of any given material to the applied magnetic field will depend on that material and the atomic and molecular physics of its constituents. This predicts the total magnetic moment of the block of material. In some cases, the internal field is increased. These are the para, and in others it's decreased. These are the dia. In both cases, the effect is small, and remember that para tends to be greater than dia. If we look at minerals, for example, lodestone, which is called magnetite by the geologists, it is the starting point of the study of magnetism because these were found in nature. I think the earliest case was many centuries ago by the Chinese. And so here you have a lodestone, fairly big one, and these are tools that are made of steel, and you can see that they're attracted strongly to the lodestone. The degree of magnetization of a lodestone is, of course, very dependent on the thermal history of that material. Ferromagnetism, like para, requires atoms with unpaired spins. If you have unpaired spins, you're going to end up with a dipole moment per each atom. But in addition, there is a very strong interaction between neighboring dipole moments. This is a quantum effect, and it involves what is called the exchange interaction. And this is an interaction between neighboring atoms. This results in a collective ordering of the magnetic moments. From this ordering, you end up getting domains, and these are regions of the material, three-dimensional regions, that are formed that consist of small patches that have a net strong magnetic moment. So therefore, the local capital M, which is the density of these dipoles, exists, and each domain has nearly permanent capital M, and is locally much, much larger than for a paramagnetic material. Remember, we said paramagnetic materials do not interact. So ferro, we have lots of interactions to give us these domains. So I show here just a cartoon of the magnetization with an accompanying dipole moment for regions of the material, and you can see here that they're basically all disordered, and so material that's been sufficiently heated to destroy interactions between the domains, and we get disorder. So as a result, we have no net capital M for the bulk of the material. Now we apply a external field, and we'll again call it B0, and it will tend to line up the domains parallel to the external field. So I show you here a B0 in this direction, and so what that does, it gets these domains attempting to align. I didn't mention this before, but the size of the domain actually changes with magnetic field. It tends to grow a little bit. But the important thing is that you have this very, very close to high alignment where we in the material, so that gives us a large capital M. Another property of ferromagnetism is that when you remove the external field, so you get rid of this, a significant fraction of the maximum value of M remains. That gives you a permanent magnet. That's what happens when you magnetize a material. Remove the field, you're left with capital M, giving you a permanent magnet. So the enhancement of the applied external field is very large. With the total magnetic field inside a ferromagnet, you can get up to 10 to the 3, 10 to the 4 times greater than the applied field. What that means is the permeability of a ferromagnetic material is large, and it's not constant, since neither the total field, B inside, or the magnetization stays constant. If you increase B sub 0, M tends to increase linearly with B0. This relationship between M and B0 is not unique. It depends on the previous history of the material. So it could depend on the temperature treatment, it could depend on what kind of field it's been in and how that field has changed. And this behavior is called hysteresis. In a ferromagnetic material that has been heated, the domains are oriented randomly, and therefore you have very small magnetization, if any. When you apply an external field, the dipoles at the edge of the domains feel a more intense torque, and the net effect is to cause the domains with a capital M parallel to the applied field to actually grow. So in other words, you have a domain, and when you apply the field, it tends to want to grow in addition to align. If you apply a strong enough field, unoriented domains try to align by rotation of capital M with the applied field. When all the domains are aligned, you're saturated. You have the material with the largest M that you can get, and so therefore the B inside has its maximum value. To magnetize the material, we set up a coil so that we can get almost a uniform B0 or H, and this coil would surround the material. Remember that H is directly related to the free currents. As the current is increased, H increases, and so does the capital M, the magnetization. Eventually we reach saturation. M does not increase further. Okay, so then B can increase only slowly due to the first term, which is this term here. it will increase because of H increasing. But because M is much, much larger than H, it'd be very difficult to see. So the B behaves as if it's saturated. Okay, now if you begin to turn down the current, which means you're decreasing H, the domains remain partially aligned. So only when H reverses are you able to get a substantial decrease in M. Thus the relation between B and H is not linear. Worse, the value of M and therefore B does not depend only on H. It depends on the history, and that's what we said before. This phenomenon is called hysteresis, and so if we now plot the B inside versus the applied H, it might look like this. So here we have the magnetic material. We place it in a solenoid, say, and we put current through the solenoid. You can change I and therefore change H. What is H? Well, remember B0 is related to the current with this equation here. N is the number of turns per unit length. Remember B0 is also equal to mu0 H. So divide both of these equations by mu0, you get the equation for H. It doesn't have mu0 in it, it's just the number of turns per unit length times I. So this is what the hysteresis curve looks like. So let's say you started with a totally unmagnetized material because you've heated it for a long time and it's come to 0, capital M. Now remember that M and B inside are related, and M is much larger than H. You start up this curve and the domains are aligning and you end up reaching close to a saturated value up here. If we look at this, then we have this maximum value up here, and by the way, I said this axis was either B0 or H because they're proportional to each other. Right here, B0 is equal to mu0 H. So you come up to this saturated value and then you reduce the current, so therefore B0 or H are decreasing. Notice what you have here. At 0, B0, so you've turned off the current, say, you still have magnetization, and that's what we mean by having permanent magnetization. And so this would be a residual M or a residual B inside that exists. In order to get 0 M, we have to actually reverse the B0. So we turn the current around and we force this alignment to go away by getting down here. But remember that you have a M and you have an applied H to give you this 0 value. What's happening then in terms of domains is that they're lining up here like this, and then you're forcing them to react to this change. They're trying to flip. In this value here, they're partially aligned in one direction, partially aligned in the other direction, and so the magnetization ends up being 0. If you continue to apply H in the opposite direction, then you just get the inverse behavior of this curve up here. It comes out to the saturated value here. Okay, so then you reduce the current, you reach a point that is equivalent to C, except in the opposite direction. So you have a permanent magnet with the opposite dipole direction. And then, like I said before, if you continue to apply that field, you end up with 0. Remember here what you've done is reversed the direction of the current, and so therefore the direction of B0. Any point over here represents a applied B0 in one direction, then every point on this side here represents reversing that direction. This is what you call a hysteresis curve. I would not claim that this curve on one trial versus many trials is exactly the same. It may turn out that by flipping and flipping and flipping, this curve might change a little bit. If we look at this in terms of applied H versus time, you might have the following. So you go up the curve, you reach this value of M that is as high as you can get, and that's called the saturation magnetization. Then you come back down and you reach the intercept at 0 H, so you have no current through the coil. This is your remnant magnetization, so m sub r. You continue and you end up with an intercept here that is the h that is required to give you 0 capital M. It has a name, and it's the cohesive force. So it's the field needed to bring M back to 0. And so then you continue on and you get the loop, the hysteresis loop. One thing about the hysteresis loop that we don't have time to go into now is that the energy it takes to go around this loop is energy that's dissipated. And it's dissipated by heating up the material. And so if you do this very, very rapidly, you end up getting fairly high temperature in the material. What that total energy, or the energy lost due to going around this loop, is equivalent to is the area contained inside the loop. And so if you have a material that has a big fat hysteresis loop versus one that has a very skinny one like that, this loses less energy than this one. And I guess I should have drawn this so that they have the same values of saturated value. These end up giving you the same m sub s's, but this dissipates a lot less energy than this. There may be reasons where you don't want that heat. It can live with this small change in the h sub c. This exchange interaction, which gives you the ferromagnetism, decreases with temperature. And so as you go up in temperature, then the saturated magnetization, which is called m sub s, remember, if you have the E exchange much larger than kT, you have ferromagnetism. But as a function of temperature, this will go down and can end up with 0, and that's the ferromagnetic Curie temperature. Remember, this is material specific. If you have paramagnetism, you have this exchange being less than kT. If you take your magnetization curve and look at what happens to this curve as you decrease m sub s due to an increase in temperature, then your hysteresis loop will get smaller. This maximum m sub s decreases with temperature, and it's this quantity here that's being plotted. So as you go up in temperature, this hysteresis loop gets smaller and smaller until it's basically 0. When you hit 0, so in other words, it's just sitting here at 0. You can't even see it. Wiggle, wiggle. And that's at the Curie temperature. Let's look at some magnitudes. If you want to see what size they are in terms of the value of M, if you look at the dipole moment per atom, it usually has a magnitude on the order of 10 to the minus 23. And remember, the units of dipoles is amps meter squared. Take the atomic density of, say, a metal. It's about 10 to the 29th atoms per meter cubed. If you took this dipole moment, this density, you can calculate then the magnetization if they were all aligned. And what you end up with is 10 to the 6 amps per meter. If you change that to a value of B sub r, that's equal to about 1 Tesla. Typical permanent magnets have internal fields of about 0.3, so they don't make the perfect alignment that we just predicted. Here are some other values. These are some of the biggies. The residual B inside at the crossover of the axis, so in other words, you remove the current, so this would be what's left. So if you take this value here for different magnets, this ceramic magnet, I don't know the composition, has a B of 0.4 Tesla. If we go to alnico, there's two types of alnico with probably different compositions. You can see that we're very strong. We have the value of near 1 Tesla. Then you go to the samarium cobalt magnets. They also have very high B residual. Some of the strongest permanent magnets are the neodymium iron boron magnets. If you have to buy these, this is sufficient B residual. These are much cheaper than the other materials, partly because these elements are expensive. The other thing to consider is the strength. You can pound on these things. These are fairly brittle. So that if you have an application where vibrations and stresses are high, you're probably going to be stuck with the alnico. The composition of alnico is shown right here, and the reason it's called alnico is aluminum, nickel, cobalt. And you can see they're high in the magnetic materials, nickel, and they have a non-magnetic material. They have a little bit of iron in them. So what material science people have done is just kept trying all the various compositions, measuring B residual, and finally working that up to the highest value that they can. This data, by the way, is from Commercial Magnet Company. I want to give you another application of ferromagnetic materials. This has to do with magnetic shielding. So if you're an experimentalist, listen up. So one of the important uses is this magnetic shielding, and what it is trying to do is create a volume in space where the magnetic fields are reduced to very small values. You can't get to zero, but you can come close. The advantage of using these is you can do this over a larger volume than Helmholtz coils, which we've talked about before. The Helmholtz coils, you have these two coils like this, and you run opposite currents through them so that the field right in the center is zero. So this one cancels this one to give you zero. One alloy that is very common is called mu metal. The reason for that is it has a high magnetic M. It's very soft and it's very malleable, so you can shape it around your experiment. Mu Metal is a company, actually. You can find it on the web. This is what's called a soft ferromagnetic material. It's just exactly what I showed you before. A hard material has a very broad hysteresis curve. The soft has a very, very narrow. What this means is that you can change H by a very small quantity, and this changes very rapidly. So that's going to be useful in applications as follows, that if you have the mu metal shielding your experiment right here, if H out here is changing, some person with a big iron belt buckle comes up here, changes H, this will respond with very, very small changes in H. The way this works is not by blocking the H, but by basically shunting it. This is a simulation by mu metal that shows a cylinder surrounding your experiment right here. So the cylinder comes out of the page. Here's your H applied. So it could be uniform initially. But as you put this material into the field, what happens is the field lines come into the material and are shunted around and then leave over here. For a limited value of H, you're able to keep this region here free of lines. In order to get this to work, you have to enclose the experiment with the mu metal. In order to close, you have to have some kind of a shape. These are volumes that might be interesting. A sphere would be very difficult to make, but if you could make it, it would be good. A cylinder is good for blocking fields that are moving along like this. Because of the simulation here, you can see it's going to work, and because of the shape of the surface. The thing that you want to do is cap the ends, because you may have components of the field that are not exactly like this. You'd like the end cap to help you block the external fields. This is the most efficient. This would be next. Normally you end up building some kind of a box. And the only problem with this is the way I built the box with Mathematica. It's perfect and it has these very sharp corners here. That's bad. So what you'd want to do is build a box with rounded corners. So you'd have to look at the geometry of that, because you really want this thing to have a rounded corner. And the reason for that is that if you have an abrupt change in the angles of the surface, you get flux leakage into the volume. And so that destroys the effect that you're trying to produce. Just for your information, this mu metal is very soft, and you know metal shears. You can cut the material with this and shape it and bend it to be the shape that you want. And I just comment, good luck making a sphere. So here's a commercial box that you can buy. I didn't mention this, but if you make this box in layers, you get a collective effect so that the B field goes down and down and down as you approach the center. This box has 5 layers. Each layer is about 5 millimeters thick. The shape is cylindrical with removal of 5 lids. So here's the cylinder here, and the way you enter this region is they have these little suction cups that you can attach to the window and remove it from the cylinder. So that gives you access to the region that you're trying to do an experiment. They have access holes for inserting cables and wires. Normally you need those to do your experiment. If you want to do the best job of getting rid of the Earth's magnetic field, is that you want to tip this so that one of these surfaces of the cylinder is pointing towards the direction of the field. That will reduce the field inside to over 15,000 times. Here's the URL for this particular box. There are other manufacturers, but I just wanted to show you what they look like. There's other applications. If you remember as a kid you made electromagnets, so here's a nail with a coil, so this would be analogous to a solenoid, and you put a battery around it, and because of the material you have here, you don't have very much residual magnetism. So in other words, you magnetize it. If this is the 0 here, didn't quite hit it. But as you go up and down, it goes through 0 approximately. So in other words, this curve is extremely narrow, like that. So you don't have much residual B. If you make this out of very soft iron, it will have a residual B, and so you make a permanent magnet. So this shows the effect. In a later talk, we'll show that the field outside is proportional to the M that you produce inside. If you want to produce a field out here that's intense, so you may have an experiment that you can't put inside or whatever, the magnetic material will greatly enhance the field out here. If you take two magnets, you remember we found how two horseshoe magnets or magnets, bar magnets for example, how they attract. It has to do with the strength of the field and the gradient of the field. The bottom line is, with a magnetic material, you can produce a much higher B field outside as well as inside. The B field lines behave like I show you here. They're continuous inside and form these loops, so that for every field line inside, you have a field line coming out in a continuous way. So right at this point right here, you have the strongest external field. I don't know if anybody uses these anymore, but this is the old electromagnet that was used for experiments. So right in here you'd have very intense magnetic field. This would be a north pole, for example. This would be a south pole. These levers here actually move the poles back and forth. The reason that these are not used very often anymore is because you can use superconductor coils to get these very intense fields without the magnetic material. Other application is transformer cores. You form a structure like this of a material with a high mu. If you run current through here, you can generate a field over here. The reason that this will work is because this current will be a function of time. And the only way you'll get a induced EMF over here, voltage over here, is if you have a time-dependent current. And this will be time-dependent here. And this has to do with Faraday's law, which we'll study soon. You've seen tons of these. These are the gray boxes that are up on the telephone poles, or the power poles, excuse me. And the power pole is, this wire here is at very high voltage. And so what you need to do is drop that voltage down to a lower voltage that you can use for your house. And so they'll have these transformers up here to do that. And that's dependent upon the ratio of these numbers of turns. The disk memory is currently still dependent on magnetic phenomena. So what you have is a writing device where this is very, very small, and it can create flux lines that pass through the material, and by orienting the field you can put into the material alignment that is either up or down. So for example, this could be a 1 and this could be a 0. And so that's how you store material. This is a layer that's just supporting this, and this thing's spinning at very, very rapid velocities. You're running this where the head is running back and forth, generating these structures. And of course the read head would then sense these magnetic moments. In terms of size, this is not the world's record, but this dimension here is 5 microns, And so this is a domain as measured with a magnetic force microscope. And so as the tip of the microscope goes over here, it sees a force that acts on the tip and it lets you image the magnetic moment that is associated with its volume. This is, by the way, a figure that's produced by a AFM, Atomic Force Microscope Company, Digital Instruments. Just to finish then, I wanted to just very briefly mention two other types of magnetic materials. This is the case of the aligned ferromagnet. There's another type of ordered structure where the domains form this pattern here so that they're in opposite direction as you go across the material. So initially, when these were disordered, you put it in the field and you have these ordering that's in the opposite direction. And so that's called anti-ferromagnetism. If you heat this material up, then you start to disorient this material, but it still stays, it tries to stay with this type of order here. There's one more, and that is you have something that's close to the anti-ferromagnetism, where one direction is favored over the other. So you end up having an M. See, here you have an M equals 0. You end up having an M because this one's bigger than this one. So that's called ferromagnetism. Now, I hate to tell you, but these materials are extremely important technologically. And in fact, this ferromagnetism is used in disk storage, partly because you can switch this very, very fast. The other thing I wanted to show you is that in terms of size, the density of information is going to be dependent on the size, let me go back, of these structures here. If you can make them smaller and smaller, you can put more information on. This is, I think, the current record produced by IBM, and this is a scanning tunneling microscope that shows you this would be the bit, and it consists of 12 iron atoms. This was assembled on a surface by using one of these tip probes that will hang on to the atoms and then you can drop it. The domain here is actually anti-ferromagnetic. You can store a bit here using the tip of a magnetic force microscope to change the direction of this material. This is a magnetic force microscope image of the atoms. This is a bigger structure here where you have different domain orientations, where this represents a 0, this is a 1, 0, 1, 0, 0, 1, 1. And you can see that in terms of the width of this, so it's this width here, it's just like above, it's 2 atoms wide. So if you wanted to, you could say that storing information in this direction is only 2 atoms wide. You're stuck with this size here because, I didn't say this, but the stability of the magnetic properties of the particle, this collection of atoms, goes away if you make it smaller. So this right now is the smallest stable bit that has been made. Can we beat it? Well, I would say leave it to IBM. They're certainly trying. I don't know if you could imagine this picture here compared to this picture here. This would be roughly 2 microns. This is roughly 2 to 4 angstroms. So it's considerably smaller than the one that I showed you. So next time we're going to talk about the field of a magnetized object. And it's related to the picture that I show you here. It's what is this field, for example, inside the material when you try to magnetize it. That will be related to, of course, the way that electrons behave in this material inside of the magnetic field that you produce with the coil.